So morning all, and welcome to the second lecture on variational autoencoders. Believe it or not, this is actually going to be the last official lecture that I will be doing this semester because the next two lectures are by Ben Streiner, who's the expert on GANs. After which we'll have a guest lecture by Gerald Friedland, which I strongly urge all of you to attend because it's really interesting work. We will not have a lecture on the 7th of December we will not have an official lecture on the 7th of December. I do plan to do a few more lectures on Boltzmann machines and Hopfield networks and reinforcement learning, but those are meant only for interested students to attend. Now, so let's start. Here's what we've seen so far. This is a quick recap of what we did in the last class. In the previously in the course, we've seen how neural networks can perform classification or regression. And now we've begun to look at neural networks as generative models, which can model the distribution of any data. And the idea of modeling the distribution is twofold. Typically, when we model probability distributions for data, we like to be able to compute the probability of a given sample of data, number one. Number two, we like to be able to generate new data of the kind that whose distribution we have learned. And for this reason, we like to have generative models that we can learn from the data. Now, in statistical estimation, a generative model is a functional or a computational model for the probability distribution of a given data. This is all recap from Monday. So it can be represented generically using this formula. We have x theta. This is a parametric distribution function which models the distribution of the data. So the theta are the parameters of the distribution. Now, typically, although this is just a little functional function which captures the distribution of the data as best as we can, it usually encodes a generative story for how the data were produced. We saw this in the last class. And the reason we want generative models is that we can compute the probability of observing a specific data instance X. We can also use it to generate samples that are statistically similar to the data that we've learned the model from. We saw a couple of examples of generative models. So Gaussians, for example, this is what I call a one-step generative model, where you just draw a sample and that's it from the distribution, or a multinomial, where you just roll a dice a bunch of times and that's it. You get a probability, you get an observation. So here, the process of generating an observation is a one-step process. We also saw multi-step generative models, like this one here, a Gaussian mixture, where the generating process that we model goes through two steps in order to generate an observation. In the first step, it selects one of the many Gaussians. In the second step, it draws an observation from the Gaussian. And here, what we actually see is just the observation it has drawn, but the actual process of generation is a two-step process. Or this model here, what we call linear Gaussian models. We'll get back to this again. Here, you first draw an observation from, you draw a vector from an isotropic Gaussian, then you linearly transform it, and then you add some noise to it, and that gives you your final observation. So in all of these cases, you're actually modeling a probability distribution. Here you're modeling a Gaussian, you're modeling a Gaussian mixture, and wow, my PowerPoint has gone into spinny mode. So here, the underlying process that is being modeled is also a Gaussian, also has a Gaussian distribution, because what goes in is Gaussian. It's linearly transformed. So the result of the transformation is Gaussian, and then you add some Gaussian noise. So the entire thing remains Gaussian. I fear my machine has frozen. So I'll wait a few seconds. I may just have to reboot PowerPoint. Any questions so far, guys? Anything from the last class? No? All right. So I'm assuming you know all of this. Now, do we remember how we learned the parameters of these distributions? We want to learn these generative models. What was the formulation we used to learn the parameters of these distributions? Anyone? Guys?
Maximum likelihood.
Maximum likelihood. That's what we used, right? So and what was the underlying principle behind maximum likelihood? Anyone remember that?
I think you talked about the product of all the probabilities.
So you're too faint. But then we said we made a. Yeah.
It found that the address is not.
The deep learning world is so boring.
Yeah, so we basically said the world was a boring place, that whatever you have observed is very typical of the process. So the maximum likelihood estimation process model framework was based on the hypothesis that your data are very typical. So given a choice of many distributions that you can attribute to the data, you chose the one for which the data were most typical, the data were most likely. And so the maximum likelihood estimation process said that given a collection of observations, you choose a parametric form for the distribution you assign to it. You chose the parameters such that the log likelihood, the log probability of the observed data was maximized. And if your data consists of a large number of independent observations, then you maximize the sum over all observations of the log probability of the individual observations with respect to your parameters. And the resulting parameters are your best estimate for the parameters of the model. So here, for example, you would choose this distribution as the one that best explained these data. Here you choose the red Gaussian as the one that best explained the histogram you've seen there. Yes, Ravneet?
So does that mean you just take your data that you already have and produce probabilities for each class given the data?
So there is no class. You're just trying to model the distribution, right? For example, here.
I mean, just compute the probabilities of the distribution directly from the data you have given.
So again, you wouldn't know the theta, right? So for every possible value of theta, you would compute the log probability of the data that you've got and choose the specific theta for which it was highest. For example, in the case of the Gaussian, theta is going to be be the set of means, be the mean and the variance of the Gaussian. Those are the parameters, right? So here, for example, I've shown you 3 different Gaussians. You would compute the log probability of your data using each of the 3 Gaussians and choose the Gaussian for which the log probability was highest. That's going to be this red guy. Does that make sense?
Okay, thank you.
Yeah. So that's basically it. And then we saw that maximum likelihood estimation from incomplete data is a problem. For example, if you had data of this kind, where you had many vectors and the vectors were missing many components, then you cannot actually estimate the means and variances of the Gaussian distribution directly from these data because you're missing components. So also, if you had a process of this kind where you had like a Gaussian mixture, you first chose a Gaussian and then drew an observation from the Gaussian. The generating process first chose a Gaussian and then drew an observation from the Gaussian. The complete description of the data would require you to know which Gaussian was chosen for every observation, but that information is missing. You only see the final observation. And so once again, you can't really compute the likelihood. It's not easy to compute the likelihood of the data in a nice closed form. Why so? Or to maximize the likelihood of the data in a nice closed form. Why so? Because the maximum likelihood estimate must only consider the data that you have observed. This is the only reality that you've got. You cannot be putting in any hypotheticals in here. But these data are incomplete. Here, for example, you haven't seen these black components. Here, you haven't seen which Gaussian was drawn. And so the the way you would compute the probability of just the observed components is to write out the probability for the complete data, including the missing values, like the identity of the Gaussian here, or the missing components here, and then marginalizing out the missing components. And this causes, so if all you observe with the data O, which are the observed components here or the observations here, then the distribution itself is over the complete data, which includes the observed components and the missing or hidden components. And so to get the probability of just the observed components, you would marginalize out the missing components by summing or integrating them out. As a result, when you want to compute the maximum likelihood estimate for the parameters of the distribution, you end up with this term, which has a log of a summation or an integral. And these things don't have nice closed form solutions to find to optimize, that you can maximize with respect to these parameters. And so you can't really get a clean instantaneous solution. You need to have instead an iterative solution. And so for the iterative solution, we introduce something called an empirical lower bound or an elbow function, which was guaranteed to always be below the actual log likelihood of the data. Again, you remember this. Our elbow function, if the log likelihood of the data had some form of this kind, the elbow function had the property that it was always going to be below it, and you could make it touch the log probability function at any point that you wanted. And so the elbow function itself had this form, which was the expectation of the log probability of the complete data taken with respect to the conditional probability of the missing components given the current estimate of the parameters of the model, plus an extra term. Right? So we saw that if we iteratively maximize this guy, so if we maximize the elbow and then reconstructed the elbow at the new estimate and maximize that, if you kept doing that, you're guaranteed to get to a local maximum of the log likelihood function, which should give you a decent estimate of the parameters. So this was our expectation maximization algorithm. So the overall process for EM was that we defined this auxiliary function, which is essentially the elbow plus a term that doesn't depend on theta. And you iteratively maximize this elbow function. You compose the elbow, you maximize it with respect to theta, then you recompose the elbow at the new estimate of theta, then maximize it again with respect to theta, and you repeat the process until it converges. And that's going to give you a local maximum estimate for the parameters of the distribution. So that was the math. Practically what this meant was that when you got data with missing components, like here, or missing variables, like in the Gaussian mixture case, what we did was to complete the data. We completed the data by filling in the missing components with every possible value that they could take in proportion to the probability of that value. So each vector over here became this expanded set of complete vectors. And then you went back and re-estimated the model parameters from these complete data. So also each vector over here became a set of vectors, complete vectors, where each of them now also has the identity of the Gaussian. And then you went ahead and re-estimated the parameters of the distribution from the completed data. And then once you got the parameters, you had a new way of completing the data. So you'd construct a new bank of vectors and repeat the process. So this completion of the data, there were two ways of doing it: by explicitly considering every possible value for the missing component, or you could complete it by sampling the values of these missing components from the posterior probability distribution of the missing values given the observed values. So this was your EM algorithm. How many of you remember all of this? Raise your hands. This was from the last class. So that's 35. A good many if you haven't actually gone through last class's lectures, or maybe you don't recall this. But I'm just going to build up off of this. So you better be awake. Then finally, after the class was over, in the extended lecture, we spoke about missing principal component analysis. Everybody is familiar with principal component analysis. Here's what we do. Given a centered set of data, shown by these black dots, we try to find this principal subspace, which is a linear hyperspace, a hyperplane, such that when you project all of the data instances onto this hyperplane, then the error that you get from approximating the data by their projections, which is the length of these black lines, the total squared error for all of the training data are minimized. So what we do is to sort of scan through all possible planes until you find the plane for which the squared lengths of all of these black lines, these error squared, some squared error is minimized. And that is your principal subspace. Now, we saw that there's a nice closed form solution for this. We're all familiar with PCA. PCA always has a closed form solution. But in the last class, we also saw that PCA could be iteratively estimated. The way you would do it is this. Say you're given some training data, X, which consists of a collection of vectors. So this is a matrix. Each X over here is a vector. Then the iterative solution said you'd begin by initializing some guess for this for the basis of the subspace. So basically for the subspace itself. Then you would project the data onto the subspace. And so if you'll remember this from the last class, the way we did it, if I had some data points, I'd initialize my subspace somehow. This is my center. And then I'm going to approximate each of these guys. Say, let's say I have some point here. By there, I'm going to compute my projection on the subspace. This is step one. So if my data, the set of data were my matrix X, then I'm approximating them as W times Z, where W is the set of bases for the subspace, and Z is the position on the subspace, the projection. And so if I've initialized W, I can say Z equals pseudo inverse of W X. Now the formula is not important, but the point is that you can project it onto this guy. Then subsequently, we let this thing rotate so that the total squared length of these, projection errors is minimized. So when you rotate it, this guy moves here, so you're going to get this length. This guy moves here, so you're going to get this length. This guy would move here, so you're going to get this length. This guy would move here, so you're going to get this length. This guy would move here, so you're going to get this length. So you'd let the plane rotate so that the squared length of these lines is minimized, and that gives you a new plane. And then you would go back and project the data back onto the new plane, like so, and repeat the process. We said we could actually keep iterating this process and it would converge. So this was a two-step process. Given W, initial estimate, you'd find the best positions Z on the plane. Then given the position Z on the plane and the X, you could go back and re-estimate your plane. So if you repeat the process, this is guaranteed to find you the principal subspace, with one caveat that rotating or stretching the plane doesn't really change the solution, the total error, because the error itself remains the same. And so to get a unique solution, we saw there were two options. You can constrain these W to be orthonormal, or you can constrain the position on the plane to be a standard Gaussian, which is to say, have a Gaussian distribution with uncorrelated Gaussian distribution with unit variance. And so the outcome of that was that we figured that this looks like an autoencoder, right? This is really just an autoencoder with linear activations. And So this told us two things. First, an autoencoder with linear activations actually performs PCA. Second, if Z is constrained to be a Gaussian, that gives me the same plane. So this really tells me that the decoder of the autoencoder is a generator. It's a generative model. And so we learned that there is a generative story behind principal component analysis. The generative story is like this, that you first draw a vector from an isotropic Gaussian. Then you transform this vector using a linear transform. So your Z becomes x hat, where x hat equals A times Z. And then once you get this x hat, you add to it some noise, but the noise has a property that the noise is orthogonal, always orthogonal to the plane on which the vectors of A lie, and you add that noise to x hat, and that gives you your final data observation x. So this is the generative story behind PCA. Or alternately, you can say that you start off with an isotropic Gaussian. This linear transform stretches and rotates the Gaussian so that now you get, so basically this linear, if you have a k-dimensional Gaussian and the linear transform goes from k dimensions to n dimensions, this linear transform stretches and rotates this k-dimensional Gaussian and implants it as a k-dimensional hyperplane in the n-dimensional space. And so in order to generate any point, you first take a Gaussian step on this hyperplane, and then you draw a second noise, which is also Gaussian, but which is always orthogonal to this hyperplane, and then you add that noise after having taken this Gaussian step, and that is your final observation. And so Fz is the variable that you draw from this standard Gaussian. Then A times Z, which is x hat, will have will also be Gaussian, and because this has zero mean, the distribution of x hat will also be zero mean. And also, this is just a property of Gaussians. If x is Gaussian with zero mean and unit variance, then A times x is going to be a Gaussian with zero mean, and the variance is going to be A times A transpose. This is very straightforward to show. We won't go through the math. So x hat is Gaussian with this distribution, and then you add the noise to it. So the noise is, of course, uncorrelated to the position on the plane. So overall, what we find is that because x is being drawn from a Gaussian and E is being drawn from a Gaussian, the distribution of x, because z is being drawn from a Gaussian and E is being drawn from a Gaussian, the distribution of x is also Gaussian. It has zero mean, and the variance of x is going to be a hat, which is the variance of x hat, plus the variance of the noise, which is d. And what PCA does is to say that the data x has a Gaussian distribution, and that the probability distribution of x is a Gaussian, a thin Gaussian, which lies mainly close to a hyperplane, which is your principal subspace. And that all the correlation between the different components lies entirely on the subspace, and any variation of the subspace is uncorrelated. So PCA actually assumes, it actually models a Gaussian distribution. It says the data has a Gaussian distribution of this kind, where the distribution itself lies very close to a subspace, to a plane, thin plane. So it's like a thin Gaussian lying very close to a plane. And so when we perform PCA, what we are really doing is to estimate the basis for the principal subspace, which is this matrix A, and the variance of the noise orthogonal to the principal subspace, which is this covariance D. And PCA itself actually performs maximum likelihood estimation. Although nobody ever told you this, the standard formulation that you have for PCA is nothing more than maximum likelihood estimation of these parameters. Is there a question in chat?
Yes, there's a question in chat.
What's that?
The question is, so in the case of PCA, the dimension of Z should be strictly less than dimension of X.
So Z is the dimension of the principal subspace. So it's a subspace. Yes, right? So again, the key point is this, right? This is the PCA has a generative story. It says that I have this principal subspace. I take a step on it, a Gaussian step on it, and then I take a Gaussian step off of it. That's the story that we've got. And so the actual estimation says that if you follow the story, then the probability distribution of X is this Gaussian here. I can compute, given a collection of data, the parameters are just A and D. I can perform maximum likelihood estimation on these using this distribution. And if you do it, you'll end up with your standard PCA eigenvalue decomposition estimates. So PCA is actually maximum likelihood estimation. But in the process, there is missing information about the observation and information about the intermediate steps that were values drawn in generating any observation. So when you perform PCA, you're only given X. You're not told X hat. You're not given E. You're not given Z, right? So you need at least one of these variables. If you know Z, you can figure out X hat. If you know E, you can figure out Z. So let's assume Z's are missing information. So there is missing information about how X was drawn here. We are not being told Z. And so here's what it is. What this means that the reason searching for this principal hyperplane becomes an iterative, it becomes challenging, is that for every data point, if you knew exactly where the projection lay, so I just told you this distance for every data point, then you can trivially find out what the plane is. The problem is this is not given, which is why you end up with the estimation problem, where you have to do the eigenvalue decomposition or the iterative solution. But if you knew Z for each X, estimating A and thereby D is going to be trivial. And so, and how's that? I won't actually work through the arithmetic, but it turns out that if I gave you the Z for every training instance, then here the Z is known. You just have to estimate A and you have to estimate D. If you go through the maximum likelihood estimation procedure, you're just going to find that your estimate for A is simply the data matrix times the pseudo inverse of the matrix composed from the position vectors of the data instances. Very simple. It's very close. Now, because Z is not given, we either we need a more complex solution. And in the specific form, when we use an iterative solution, here's what we do. We start off with an initial estimate for the plane. Then if I give you an initial estimate for the plane, I can estimate the Z's for every data vector. Because if I gave you these data vectors, and I told you that this is my initial estimate for the plane, then it's very easy to compute the perpendicular drop on the plane for the data vectors. So the first step that we do is estimate these Z values for each of the data vectors. Then once we are given the Z values, we fix these Z values and re-estimate the plane. So, but then once we re-estimate the plane, we can go back and re-estimate the Z's. And this is the iteration that we follow. And in fact, as we saw, this just ends up being En, right? So basically, the iterative solution for PCA is an expectation maximization solution performed on the generative model that PCA actually represents. And it gives you the solution. So finally, we saw that we can improve upon PCA. The problem with PCA was this. It's limited. it assumes that there is a principal subspace, that you're taking a Gaussian step on the principal subspace, and then you're adding some noise to the data that is orthogonal to the subspace. And in real life, we know that noises don't need to be, orthogonal to the data. For example, the noises that corrupt speech. If you just close your eyes and listen to the world around you, you can hear voices in the wind. You can see faces in clouds. Noise often looks like the data that you are trying to model. And so random noise doesn't have to be orthogonal to the data. It can be in any direction. And so we improved upon PCA, and this gave us the linear Gaussian model. This is still the same model. We are saying that you start off with a value which is drawn from an isotropic Gaussian. You linearly transform it, and then you add some noise to it. But now instead of being always just orthogonal to this plane, the noise is a full rank noise. It can lie anywhere in the space. And the only additional assumption we'll make is that although the noise is full rank, it's uncorrelated, meaning the X component of the noise is independent of the Y component of the noise. But the noise is Gaussian, it's full rank, and you add it to X hat. So this is a generalization of PCA. And now the PCA model basically says that I first take a Gaussian step on the principles. The LGM model says that I take a Gaussian step on the principal subspace, and then I take a Gaussian step off the principal subspace. It is still modeling the distribution of the data as being very close to a subspace. You're still modeling the kind of distribution that this model is capturing is still a Gaussian. It's still a Gaussian that's very close to some thin subspace. It's the only distinction is in the assumption you make about the noise that is added to the main component of the signal of the data that lies on the principal subspace itself. And once again, here, if I add noise, so if you look at this generative model, the probability distribution of X hat, which is this guy, is a Gaussian whose variance is AA hat. The probability distribution of X is also a Gaussian with zero mean, whose variance is AA hat plus D. And furthermore, if I gave you Z, then as we saw in the last class, the distribution, if I gave you Z, then X hat is deterministic because Z is now known. So AZ is known. All you're doing is to add this constant AZ to this noise. So the distribution of X in this case is going to be basically the distribution of the noise with a constant AZ added to it. So the probability distribution of X given Z is a Gaussian with the mean now at AZ and the covariance, which is the same as the covariance of the noise itself. So these were the things we saw. And now, of course, we can still perform the same. If you want to learn the parameters of the distribution, you can do perform maximum likelihood estimation.
Bhiksha, I guess we skipped a poll at slide 21.
Okay, put up the poll. Was it a slide 21? Hang on.
Yeah, it was for the PCA bit, I guess.
Okay, just go ahead. Put up the poll. Folks, there's a poll.
Is the poll up?
Yes.
I don't see it for some reason. Yeah, I'll let the team know.
A lot of people are submitting their. So folks, by the way, pardon me for being too fast today. I have a lot to cover, and the VAE lectures should really have been stretched over 3 lectures, not 2. Okay, you have 5 seconds. All right, stop. All 4 answers are correct, right? PCA performs maximum likelihood estimation of the generative model of the data. The generative model is that in order to generate any point, the process first takes a Gaussian step on the principal hyperplane, followed by a Gaussian step perpendicular to it. So it can be performed iteratively using EM, and it assumes that the distribution of the data is a Gaussian that is centered on the principal hyperplane. So these are all correct statements. So now, continuing, what about the linear Gaussian model, which is a generalization of PCA? We just saw that it also models a Gaussian distribution, which says it's a generative model for Gaussians, which says the distribution of the data are Gaussian, lying largely on a principal hyperplane with some Gaussian fuzz. And only the components of the data that lie on the principal hyperplane are correlated with one another, which allows us to model some of the correlation between components. And so this is somewhat like a something halfway between an uncorrelated Gaussian distribution and something where every component is assumed to be correlated with everything else. But the point is this: the linear Gaussian model, which is a generalization of PCA, models a Gaussian distribution. And so you can perform maximum likelihood estimation. As before, this is the distribution that it's actually assigning to the data. If you had a collection of training data points, then you would want to perform you would maximize the log likelihood of the entire training data with respect to the bases for the hyperplane and the covariance for the noise. And this guy, because you have this ugly AA transpose plus D inverse inside the exponent, and also the determinant of AA transpose plus D, two different components which are being added, and both of which must be simultaneously estimated. This doesn't have a closed form, unlike in the case of PCA, where D was orthogonal to A, so things sort of worked out. But then, as in the case of PCA, there is missing information about the observation. There's information missing about the intermediate values in drawing that were drawn in generating any instance. If I knew exactly where on the plane the first step took me, then basically the length of this line, right? If I knew the length of this line and the general direction of this line for every one of these my training instances, if I knew the z value for each of my training instances, then I could compute the bases for the plane and the covariance for the noise. How so? Here it is. Suppose I know z for every data instance. Then because z is already known, then the only thing left is unknown as e. So the log likelihood of the total training data is going to be the sum over all training data pairs of the log probability of x given z. The log probability of x given z we saw was just this Gaussian over here, the Gaussian with the mean at az and the covariance at d. And so this log likelihood of the entire training data can be written in this form. The logarithm of a Gaussian ends up giving you this nice little quadratic. And I can differentiate this with respect to a and d, and it gives me a nice closed form solution. I actually I'm not going to work my way through the arithmetic, but if you go through the slides, you will see that it actually has a very nice closed form solution for both the principal subspace and the covariance matrix of the noise. Our problem is that z is not known for each of the training instances. It's missing. The observations are incomplete. So now we know how to deal with this. We can do this by deal with this. What we will do is to complete the data. We will start off with an initial estimate for the parameters of the distribution and use it to estimate the z for we will use it to fill in the z for every data instance with every possible value of z. So each vector is now being expanded. The missing component z is being filled in every possible way in proportion to the posterior probability of z. And then you can complete and now that you have z, you have this expanded but complete data set, and then you can just use these formulae to estimate the principal hyperplane and the covariance of the noise. And for this, of course, you need to know the posterior probability of z given x, because you want that this is the probability distribution according to which you're completing all of the missing values, right? You're completing the vectors by filling in the missing values. And because everything is Gaussian, it turns out that that posterior probability distribution has a nice closed form. Again, I'm not going to derive it, but basically, when I say that x and z are jointly Gaussian, which is what they are in our case, it means that together they have this bell-shaped distribution. So if I give you the x, if p of z given x, it's like saying I've given you that x, what is the probability of z? It's like, which means you're going to be slicing this Gaussian at x1. And that slice will also have a Gaussian outline, as you can see here. And so p of z given x is going to be Gaussian. The mean will be right here. This will be the variance. We know how to derive these, although I won't do it. And now that you have p of z given x, you can sort of complete the data in proportion to p of z given x in every possible way. And as it turns out, if you complete it using every possible value of z, the complete all infinite possibilities, although in principle you're expanding the data set out to be infinitely large, in practice that gives you a nice closed form solution because everything is Gaussian. I won't actually work through the arithmetic again, but you get closed form solutions which integrate over everything out and you get an answer, right? But what's of interest to us is the second option in EM. In the second option in EM, we won't go through this business of actually integrating and trying to work out math. We'll do something much simpler. It's easier and intuitive. We will fill in these missing values by sampling from p of z given x. So we're going to draw samples from p of z given x. And then once we've drawn samples of p of z given x, you have completed data where the z values, each vector has been extended, it has been sort of expanded into many copies of the same vector, but each with a different value of z, where the z has been drawn from p of z given x. And so now you have this expanded data set, which are of vectors which are now complete, meaning that for every x we also have a z. And now that you have the expanded data set, you can just use the closed form formula we had earlier when you had complete data and re-estimate your parameters, namely the basis of the hyperplane and the covariance of the noise. So the way we're doing it again, we initialize A and D, then we draw the missing components of the missing z value for every vector from the posterior probability of z given x to complete the data, and then we estimate the parameters from the completed data. This is EM. And so that sort of summarizes linear Gaussian models. So these are linear Gaussian models. They are models for Gaussian distributions of data. Specifically, the model, the distribution of data is Gaussian, where most of the variation in the data lies along a linear manifold. And there's some fuzz off the linear manifold. The way they model it, the generative model is this. You start off with a Gaussian random variable z, then you transform it linearly. So if the Gaussian random variable is k-dimensional, then that means you have this k-dimensional space in which the data are sort of Gaussian distributed. You stretch and rotate and linearly transform this k-dimensional space and then embed it as a k-dimensional hyperplane in the upper n-dimensional space. And then you add some Gaussian noise at every point. So basically, the generative model says now that you're taking a Gaussian step on this plane, and then you're adding some Gaussian noise. And this model can capture Gaussian distributions of this kind. They're excellent models for data of this kind. It's actually a generalization of PCA, and it's actually a better model than PCA for data, right? And PCA is in fact a special instance of LGMs, where the noise is assumed to always be orthogonal to the hyperplane. So far so good. Is everybody with me so far? Raise your hands. We haven't done anything particularly complicated. I've just introduced a very 35. So, some 60 people have not got what I'm talking about. You guys are going to have to deal with this in the quiz. So if you have questions, ask, right? Now, so here's the thing. We are modeling, we are going through a lot of painstaking effort to model a Gaussian distribution. You could have said, what's the big deal about modeling Gaussians? We know how to model Gaussians. Except here we are making a very specific assumption. We are saying that the Gaussian lies mainly close to a very thin principal subspace, a planar subspace. And so we are modeling Gaussians of this kind. And for that we use this generative model, that we are sort of taking a Gaussian step on the subspace and then adding some Gaussian noise. And the subspace, and so this business of taking a Gaussian step on the subspace is instead achieved by transforming an isotropic Gaussian through a linear transform and then adding noise. So this is the generative model for this data. And the parameters of the model are A and D. And you can estimate them using maximum likelihood. Right? It models Gaussians. But then what about data that, let me see, I have, there's a poll over here. Kushal? Yeah, so guys, here's a poll. Okay, 5 seconds. All right. So all 4 statements are true in this case. The linear Gaussian model is also called factor analysis. We saw this in the last class. It models the distribution of the data as a Gaussian centered on a principal hyperplane. And the generative model is that in order to generate any point, the process first takes a Gaussian step on the principal hyperplane, and then you add Gaussian noise to this point, to the value you arrive at after taking that step. The parameters of the distribution are the bases of the hyperplane and the covariance of the noise. The parameters can be estimated if you knew the location of the first step on the principal hyperplane in the generative process for every data point. Unfortunately, you don't know it. So the EM solution iteratively completes each data instance by sort of filling in the location of this first step on the principal hyperplane, and then using that to estimate the parameters. And then once you estimate the parameters, you repeat the process by using the parameters to go back and re-estimate or refill in the locations on the hyperplane. So that's the whole process, right? But linear Gaussian models only model Gaussian distributions which are close to a linear hyperspace. What if you have distributions of this kind? Distributions that are not Gaussian distributed close to a plane, but something more like this. So this is a distribution, or this is a distribution, or here is a distribution that's kind of lies close to a helix, right? Or this is some other ugly distribution. So for something like these, using the same form of mechanism, can anybody suggest how I can modify this model to capture distributions of this kind? Anyone? Any suggestions, guys?
nonlinear activation, intermediate activations?
So exactly, right? So all I need to do over here is, instead of starting with a Z, which is a Gaussian, and putting this through a linear transform, and then adding noise. So what this does is it takes your Gaussian and this puts it as a k-dimensional linear hyperplane in the new space. If I replace this instead by something that takes my Z, which is still a Gaussian, but then it's some non-linear function. What it will do is take this Gaussian, but instead of putting it as a linear hyperplane, it's going to sort of convert it into some kind of a sheet, right? Where your data are now distributed on this linear hyperspace, and then you add noise to it. And so the generative model now becomes that I'm taking a Gaussian step on this curved surface and then adding noise to it. And so the resulting distribution is going to have this shape. Did this make sense to everybody? Raise your hands if it did. Okay. And this is really what we call, this is a nonlinear Gaussian model. The nonlinear Gaussian model has this. You're going to, now if I want to learn the nonlinear Gaussian model, what must I learn? In the case of the linear Gaussian model, I had to learn the bases of the subspace. In the nonlinear Gaussian model, I'm going to have to learn this shape of this curved manifold. But what that really means is that I need to learn this function f, which takes a k-dimensional plane and converts it to a k-dimensional curved manifold in the n-dimensional space. So learning an NLGM is all about learning this function f. So what we will do is to find a function f that warps the lower dimensional input plane to the target manifold in the data space. And then once we've found this function, we're going to transform a Gaussian distribution on the input space, which is in some which is a planar k-dimensional distribution, and we're going to transform it to a Gaussian to a distribution on this curved manifold. Again, because of the transformation, this is not going to be Gaussian anymore. The space is being twisted, right? But you can still think of it as being somewhat Gaussian on this curved manifold. And the actual generating process says that I'm going to start off with a Gaussian distribution here. I'm going to put it through this function, and that becomes a Gaussian distribution on this bent manifold. And so every step of generation means I just take a Gaussian step on this twisted manifold. And again, remember, I'm calling it a Gaussian step, but the Gaussian step is out here because things are being twisted over here. It's clearly no longer Gaussian, right? But then having arrived at that point on this manifold, I'm going to add some Gaussian noise over here, which is some Gaussian fuzz off the plane. So this is the same model as this guy here, which as linear Gaussian models, except now we've made the whole thing nonlinear. So this is the nonlinear Gaussian model. F of z is a nonlinear function that produces a curved manifold, like the decoder of the nonlinear AE. The samples of z are placed on this curved manifold, and the actual data are produced by adding noise to the samples of z on this manifold. So here is the overall process for the nonlinear Gaussian model. The nonlinear function warps this nice planar input space into some curved manifold in the data space. And so samples drawn from here are going to be placed on this manifold, and the distribution of the samples are going to be sort of distributed according to this guy. So if you look at the highly dense regions of the Gaussian here, then this portion of the space is going to get transformed into something over here. So you will find a high density in the regions corresponding to the high density regions out here. You're going to find a low density of data points in the regions corresponding to the low density points over here, because this Gaussian has been sort of bent by this function f and placed on the curved manifold. And the final observation, of course, is you get this, you go on this closed manifold and add some noise. So here is the overall generating process. I'm going to draw some sample to generate a single observation x. I'm going to draw a sample from my Gaussian. I'm going to transform that sample through f of x, which is going to place it maybe on this point on the curved manifold. And then I'm going to add some uncorrelated noise to this point, which gets me to the point x. And so this process, if you take a scatter of points, if you take many points from Z and put them all through this process, the eventual scatter is going to look something like this. These distributions can be very complicated. They can they can be viewed as lying close to some k-dimensional surface, which could be something like this, or even a helix in the data space. And in fact, f of z equals az is a special case of this nonlinear Gaussian model. And this k, that's simply the dimensionality of the principal manifold on which the data are assumed to be close to. So here in these examples, k is 1 because these are two-dimensional data, but the principal manifold is just a line, right? Even for the helix. And so the key problems here are trying to identify the dimensionality of this manifold, having a function that can transform this k-dimensional linear surface into this k-dimensional curved surface in the output space, and then being able to estimate it. So here's the whole process of designing LGMs. You need to guess the dimensionality of this manifold. This is the dimensionality of Z. Then you need to choose the right function that is capable of learning the shape of this manifold. In the case of linear Gaussian models, it's just a linear transform. Here it's much uglier, right? And so this is going to be the manifold warper and for us, this would be a neural network. And so that's going to transform our Z, and then you add noise. And so now a scatter of points out here is going to end up representing a distribution of this kind. And so when we speak of learning an LGM, you are given a collection of training data. You want to estimate the parameters theta of f of z. You also want to estimate the covariance of this noise and the distribution. And this actually is really just a generative model that actually models the distribution of your data, and the specific distribution that it represents is the distribution obtained when you transform a standard Gaussian through this nonlinear function and then add some noise to it. And so now when I'm trying to learn a nonlinear Gaussian model to represent the distribution of any data, what we will be doing is we will be using a maximum likelihood estimate again, just like everywhere else. And we will use maximum likelihood estimation to learn these theta and the covariance of the noise D. Kushal, I believe there's another poll here. Let's see. Okay, 5 seconds, guys. All right. Stop it. End the poll. all of these are right? So nonlinear Gaussian, again, today in today's polls, so far at least, all of my answers have been right. Nonlinear Gaussian models are generative models. They model the distribution of the data as a Gaussian distributed around a curved manifold. And the generative model is that in order to generate any point, the process first takes a Gaussian step on the manifold, followed by addition of Gaussian noise. And so the parameters of the distribution are the parameters of the function that transform a k-dimensional plane into a k-dimensional manifold in the data space, and the covariance of the noise that's added after you take a step on the plane. And this last bit is not something that I have introduced just yet, but it turns out that the NLGM is the decoder component of a variational autoencoder. So if you're wondering what any of this has to do with variational autoencoders, that's where it comes from. Now, so here are the probabilities modeled by the NLGM, right? So here, first, consider any data point. This noise over here is a Gaussian. It's a zero mean Gaussian with some isotropic noise, right? With some covariance, and we're going to assume that the covariance matrix D is diagonal, right? So just give me a second. Now, so if this is how the data are generated, I have got, first I have Z that is being put through some transform f of Z, and then I'm adding some noise, right? E, which has come from a Gaussian with a zero mean and the covariance D. Now, suppose I give you the Z. So given Z, what is the probability of X, which is this term, given Z? Can anybody tell me? Anyone? Guys? I'm waiting for an answer.
So
F of Z plus the noise.
Wait, there were two people answering. Could you please repeat that? Is anyone answering on chat? Folks, I'll wait for the answer.
F of Z plus the noise.
F of Z plus the noise is, what do you mean by F of Z plus the noise? So this is, I want the probability distribution here, right? So what is it going to be? Remember,
I think
X
it's going to be
X equals F of Z plus noise, right? So what is the probability of X given Z?
it's going to be the probability distribution of that nonlinear function fz plus some mean.
But Z is given.
Oh, it's going to be the probability distribution of E plus
It's going to be the probability
E.
distribution with the mean transferred to the mean of E plus F of Z.
Yeah, exactly.
And the covariance, which is simply going to be a Gaussian with F of Z and D, right?
Yeah, exactly.
That's easy. Nothing complex. So this is what you've got. P of F of Z X given Z. It's just a Gaussian with the mean now at F of Z. So if I want the probability distribution of X, what I'm going to have to do is P of X equals integral over Z, P of X comma Z dz. This is just your standard marginalization, which is integral of P of X given Z, P of Z dz, right? This is base rule. And this first term we just saw is a Gaussian with mean F of Z and variance D. The second term we saw is a Gaussian with zero mean and variance D, dz, right? So this is variance over Z. And now variance over this is going to be E. Right? So this is what it ends up looking like. You're going to have the derivative you're going to be integrating the product of two Gaussians, where the first Gaussian has a mean at f of z, and this is a very ugly function because f of z can be a very ugly function. And so this is not going to have a closed form. So you have this way of modeling a distribution which can give you a very ugly probability distribution, but the actual model itself ends up being very simple because all you're doing is taking a Gaussian random variable and pushing it through a nonlinearity and adding some Gaussian noise. So although this guy itself may not be tractable, this may not even have a closed form, I can still learn the parameters of my generative model easily. And how so? Assume that for every training data instance, you knew the z. So for every training data instance, you knew the z. So you know what the z was. You're pumping the z through this f of z, and then you're adding noise. So basically, you're knowing the position, relative position on the manifold. You don't know the manifold, you know the relative position on the manifold, and then you add the noise. So at this point, the only thing that's left to estimate are the parameters of this manifold and this covariance d. So let's consider the glass box solution, where for every data instance x, you have the z value. So you have all of these z's for everything. And I'm going to try to learn the model parameters from this completed data. That's very easy. So here's what I do. P of x given z we saw as a Gaussian, right? With the mean at f of z. So now for every data instance x, I also have the z. So because I also have the z, maximum likelihood estimation simply means that I have to maximize the sum over all of my training instances, where for every training instances I have an x and a z of the log of the probability of x given z, right? Because p of z itself is Gaussian, there's nothing left to estimate. And so this p of x given z is a Gaussian with a mean at f of z. And the variance is d. So the p of x given z is this guy here. This is the 1 over the square root of the determinant of the covariance matrix times the exponent of x minus f of z times d inverse times x minus f of z. Whole thing times minus 0.5. So when I take a log of this guy, I'm going to get minus log the determinant of d plus some other constants. And the log of an exponent is simply this inner term. So you end up with this quadratic. And so all I need to do is to maximize this term with respect to theta and d. And so this is going to be, if I had complete information, if I had x and z, I had the z for every training instance, then to estimate the parameters of the model, all I have to do is to maximize this quadratic term, which is summed over all of my training instances with respect to d and with respect to f, the parameters of f. Now, this is not a nice function. Although it's a quadratic, inside the quadratic, I have an f of z. So this is a quadratic of an ugly function. So it's not a nice function, but the function itself now has a closed form. The function itself is now sort of known. And it's an ugly function, but we can compute it and it's differentiable. So we can just use backprop. If I have a collection of training data instances where I have x and I have z, then all I need to do is to minimize this. It's to maximize this term over here. And this is an ugly function of the parameters theta and d. I can use gradient ascent to maximize this guy. Or if I take the negative of it, then I'm going to get half log d plus this quadratic, at which point I can use gradient descent to maximize this guy, and we know exactly how to do it. The only tricky piece here is how do you compute the derivative of this function with respect to theta, and we know how to do it. You know how to write autodiff, you know how to perform backprop. This is like saying I'm putting f of, this is literally like saying I'm putting z through f, the target output is x, so x hat must be as close to x as possible. I'm going to minimize the L2 loss between x hat and x and perform backprop, and I'm going to learn theta. Easy. We know exactly how to do this. So we know how to derive the parameters of the model if z was known for every data observation. Unfortunately, we don't know z. The data are incomplete. And so we are going to use EM. We're going to complete the data. What we will do is there are two different options again, right? We've seen this. In the first case, you can explicitly fill in the z value with every possible value it can take. You can complete the data by filling in the z with every possible value it can take in proportion to p of z given x. And then you can compute the solution using this formulation here from the completed data. The problem is, if the probability distribution of x is not tractable, the probability distribution of z given x is also not tractable. So there's no closed form solution for it. There's no way of actually coming up with nice mathematical formula which solves this. So we're going to consider option 2. We are going to draw samples from p of z given x, and we're going to complete the data by drawing samples from p of z given x. And then once you've drawn the samples, you have completed data, and then I can use this formulation out here to estimate the parameters of the nonlinear Gaussian model. So that's easy, right? Remember, again, option 1, where you consider every possible way, is always preferred if you can get tractable closed form solutions. But since we cannot do this, we're going to use the sampling procedure, which is option 2, right? So that leaves us with this problem. What is p of z given x? P of z given x, using Bayes' rule, is p of x given z, pz over px, easy. P of x, but then we saw, is this ugly formula that we cannot compute. So as a result, you know, while I sort of very happily said we're going to draw samples from p of z given x, by adding this nonlinearity on z, it turns out that not only can you not compute p of x, you cannot compute p of z given x either. The only thing you can compute is p of x given z and p of z. P of x given z is, of course, this first term. It's a Gaussian. And if z is known, the mean of the Gaussian is known, so you can compute this. P of z, we said, was a zero mean Gaussian, so this is something we can compute. But when you multiply these two guys and then take an integral with respect to z, this is not computable, right? So p of z given x is not tractable in closed form. So what can we do? We're going to try to approximate p of z given x. I'm going to say I don't know p of z given x, but I'm going to approximate it as a Gaussian. And the way I will approximate it as a Gaussian, I'll say that the p of z given x is a Gaussian where the mean and the variance of the Gaussian are functions of x. So I'm going to say that from the x, I can estimate the mean of p of z given x, and it's using some parametric function mu x phi. I can estimate the variance of p of z given x using some parametric function sigma x phi. And now p of z given x is going to be approximated by this Gaussian, which is a Gaussian over z with mean mu x and variance sigma x. And we're going to assume for convenience that this sigma is diagonal, right? And so this Gaussian, which I'm representing as q, this is going to be a proxy for p of z given x. But for this to work, this Gaussian has to be as similar to p of z given x as possible, right? But once assume that we have the z given x, then assume we know how to compute the mean and the variance to give you the best Gaussian approximation of p of z given x. Then the overall estimation problem for NLGMs is simple. I'm going to estimate the mean and the variance for q. Then I'm going to complete the data by drawing samples from q. And then once I've computed the data from drawing samples given Q, I'm going to estimate theta. But once I've estimated theta, then clearly the modified theta means that this guy must also change. So I'm going to go back and change my Q. I have a new approximation of P of Z given X. I'm going to draw samples from that again, complete the data, and go back and estimate theta and repeat the process. So here's the complete pipeline. We're going to initialize, again, these functions must be learned because these are approximators. So here's the complete pipeline. I'm going to initialize the parameters of my nonlinear transform from Z to X. I'm also going to initialize the parameters of the function that estimates the best approximation to P of X, Z given X. Then in the first case, I'm going to sample from this Gaussian, which is my approximation to the posterior probability of Z given X. These samples will complete my data. Then once I've sampled it, I'm going to estimate theta using X and Z, using the formulation we saw earlier. And then once I've estimated theta, I'm actually going to use this new theta to go back and update my phi, because as we know, every time you update the parameters of your model, correspondingly, the posterior probability distribution P of Z given X must also be updated. So this is the overall process. So what is this business of sampling from P of Z given X? You're going to be sampling from this Gaussian here. And this is just a standard trick, right? Anytime I ask you this, suppose I give you a Gaussian and I say, I want to generate samples from this Gaussian with some mean A and the variance V squared. How do we do this? The process for generating samples from a Gaussian of this kind is a standard technique. Does anybody know how you do this? Anyone? Does anybody know how you draw samples from a Gaussian with mean A and variance V squared? Any 1 point person? So are you familiar with this function that you have in Python or various other programming? Yeah. So what does it do?
Do you provide a random number as X?
And what are the properties of the random number?
Between 0 and 1?
No. So if you use rand n, which is the Gaussian guy, it's going to give you a Gaussian random variable with mean 0 and variance 1. This is a standard function in every programming language. It's easy to write the code for it. There are many, many algorithms for generating data from a standard Gaussian. Okay. So assuming I can draw X from this, how do I get a sample from a Gaussian with mean A and variance V squared?
Do you just multiply by the variance and then add the mean?
Exactly, that's it. Yeah. Trivial, correct? That's all you do. And so this is what we call the reparameterization trick. You draw samples, you draw sample Z from a standard Gaussian and then multiplied by the square root of the variance, the standard deviation, and then you add the mean, right? And so the sampling Z over here means that first, given the X, you compute the mean and the variances. Then you draw samples from this Gaussian using the form procedure here, where basically you first draw a k-dimensional vector from the standard Gaussian and then multiply it by the square root of the variance and then add the mean. So that's, and observe that the mean and the variance are going to be specific to X. So you can actually compute the derivative of Z with respect to the parameters phi, which is simply going to be the derivatives of whatever function computes this mu with respect to phi, plus a diagonal matrix with epsilon along all of the diagonal terms times the diagonal matrix with this vector along the diagonal terms times the derivative of the sigma itself. Okay, so we know how to draw samples. It's trivial. If you draw samples, now you have complete Z. So, and because you have complete Z, you have X and Z. So you have complete data. From this complete data, you can re-estimate this theta from the completed data. And for this, we saw exactly how we can do this a few minutes ago. I end up with this, because now you're only worried about the probability of X given Z, which ends up being Gaussian. You end up with this loss function, which you can minimize with respect to the parameters theta of the nonlinear function. And specifically, if you assume that the noise that gets added out here is such that the covariance, that the variance of the noise is identical in every direction, then you end up with D equals some sigma squared I, where I is your identity matrix. And then the whole loss function becomes even simpler. You even get rid of all of the matrix components of it. It's just a sum over, it's D is the dimensionality of your noise. That's D log sigma squared plus sum over all of the training instances of 1 over sigma squared. I've got rid of this half term here. 1 over sigma squared X minus f of z whole squared norm. So this loss now you can minimize with respect to theta and sigma squared trivially using background. So we know how to do this. So the real challenge now is, how do I estimate this phi? Once I've estimated theta, how do I update the parameters of the component of the model that computes the posterior probability of z given x? How do I update the parameters of this component of the model? And so I'll stop. There's one final poll here at this point. Kushal, can you pull up the poll? So guys, this poll, and then I'll pause here, and those who want to leave can leave. I'll complete the rest of the lecture. Ten seconds, guys. All right, stop it here. So again, as before, all statements are true. The decoder in the variational autoencoder is a nonlinear Gaussian model. The NLGM is in the VAE is estimated using EM, which is the decoder. Now, the encoder in the VAE is a module that generates the samples of Z needed to complete the data in order to estimate the parameters of the decoder, which is a nonlinear Gaussian model. And the encoder approximates P of Z given X to enable sampling of Z to complete the data. So these are things that I didn't explicitly mention, but this is your variational autoencoder. This lower portion is your encoder. This upper portion is your decoder. The upper portion is just your nonlinear Gaussian model, and this is what you use to sample Z so that you can learn the upper portion. The upper portion is your generative model. So I'll stop the recording here, pause the recording. Okay. Okay.
So the question was, I guess on the noise model in the VAE, the matrix D that we have for the for E, is that a diagonal matrix again?
So there is no constraint as far as the math is concerned for what D might be, but then it makes most sense in terms as a model if D is diagonal. So you always assume that the noise is uncorrelated, which means D is a diagonal matrix. And in fact, you will often make this extra assumption that not only is it uncorrelated, that the variance in every component is identical. So D is a diagonal matrix where all the diagonal components are identical. So any more questions, folks? Okay, so let me continue, right? This is going to be, so here's what we have. We want to update the parameters of this model, which is basically our QZX, which approximates the posterior probability P of Z given X. And you want it to approximate P of Z given X as closely as possible. So what we will do is to sort of learn the parameters phi to minimize the error between QZX and P of Z given X. And for this, we will define a divergence between Q of ZX and P of Z given X and minimize it with respect to phi. And following literature, we are going to use the Kullback-Leibler divergence. Now, the Kullback-Leibler divergence, there are a couple of different ways of defining it, but the one that gives us the most convenient solution here is to think of the Kullback-Leibler divergence between Q and P rather than between P and Q. So this is the expectation over Z, where Z is drawn from Q, of the log of Q over P of Z given X. So if I take the logs, this is again, these are all expectations with respect to Z drawn from Q of log Q minus log P. But this is P of Z given X. P of Z given X can be written as P of Z, P of X given Z divided by P of X. So if I expand it out, as expectation over Z, again, as drawn from Q, of log of Q minus log of P of Z minus log P of X given Z plus P of X. Again, all of this is about trying to learn this function Q that approximates P of Z given X so that you can draw samples of Z to complete the data and estimate your NLGM, right? So now, which are all that we are trying to estimate these parameters phi to minimize the error between these two guys. Let's look at which ones are functions of phi. So this first term is a function of phi, right? Q is a function of phi, clearly. P of Z, really, this is a standard Gaussian. P of Z is not a function of phi, so you can ignore this. P of X, again, this is the probability distribution of X. And so there is no Z over here at all. So this is not a function of phi. This goes away. The only thing that remains is this term. So if you want to minimize the Kullback-Leibler divergence between P of Z given X and Q of X, you have to minimize, actually, here's what it is. This term here, let's actually consider this guy. Expectation over Z of log Q minus log P actually ends up being the Kullback-Leibler divergence between Q and P. And then you retain this term. This last P goes away because it's not a function of phi. So you end up saying that you want to minimize the Kullback-Leibler divergence between Q and P of Z and minus the expectation of the log likelihood of X given Z. Now this guy over here says that you want this distribution, you want to learn these parameters such that the distribution of Z given X is as close to a standard Gaussian as possible. At the same time, you also want to maximize the likelihood of X given Z. So now this looks like an ugly piece of math. And let's sort of go through this in a little more. There's a lot of math over here, and I don't really expect you to understand all of the math. I'm just going through it because that completes the discussion. But the concept, of course, as far as we are concerned over here, must be very clear how the whole model works. So let's try the whole thing again. Here's what we have. We have assumed that the data have been completed by drawing samples of X. So we have collections of XZ pairs, right? In fact, you will have many values of Z for each X. So you can think of So the z's drawn are going to be specific to x. And now we can work with the complete data, right? So if I want to say, if I look at the log likelihood, if I look at the probability of the z given x, this is the product over all of the individual training instances of the product of the corresponding z. So if I want to, this first term is the probability of this entire z given this entire x. This is the product taken over the individual columns of the probability of this z given this x, because all of these vectors are assumed to be independent. So when I take a log, it's the sum over all of these columns. These are the completed data of the log of the probability of z given x. So this is the true posterior probability of z given x. The approximation is the sum over all of these columns again of the log of the q of z and x, that is given by this formula here, which is the Gaussian approximation to p of z given x. And what we are going to do, this Gaussian approximation has two parameters. It has this parameter phi, which tells you how to compute the mean and the variance that are most appropriate for the Gaussian for this given x, such that the discrepancy between this Gaussian here and the actual posterior probability you want to draw the samples from is minimized. And so just writing it out, I can define this as log of q of zx minus log of pz given x. This is what you want to minimize, which is the sum over all training instances of the log of zx for the training instance minus log of p of z given x for the training instance. So I'm just focusing on individual training instances here and expanding this out using Bayes' rule. P of z given x is pz times p x given z divided by p of x. That is going to give me the log of q minus log of p of z minus log of p of x given z plus log of p of x, right? P of x only depends on, as modeled by our function, only depends on the parameters of the nonlinear Gaussian model. P of x given z depends on the parameters of the nonlinear Gaussian model. This is just a standard Gaussian. Q depends on the parameters of the function that compute the mean and variance of the approximation to the posterior, right? So this parameter phi directly influences this guy, and it also influences z because we are sampling z from q, right? But this term is not related to either phi or z and can be ignored. So you end up with this law, with this term here, which is the sum over all the training instances of the log of q computed for the completed data minus log of p of z in this xz pair minus log of p of x given z in this xz pair. And again, if we're given z, you can compute p of x. That's a Gaussian. We know that, right? So this term is computable. This is computable. And this we know the function for. So the one thing that remains is how you complete the data, and we already know how to complete the data, right? This business, right? We've already chosen samples that we've drawn, so we can just use those. I have some extra stuff here on how we can draw things, but actually, let's go through that, right? So when we complete the data, remember, we were drawing z from p of z given x, except we weren't drawing it from p of z given x, we were actually drawing it from q. So I have this term here, which is summed, which is the, and this term is summed over all of my completed data. And this term is also summed over all of my completed data. But for this guy alone, instead of just focusing on the samples that I have drawn, I can imagine that I have drawn every possible value of z. And if I assume that for this guy, I assume that I've drawn every possible value of z, then this component, the summation for this component of it ends up being an integral over z. The summation is over only the observed data x. This ends up being an integral over z. For this one, it ends up being a sum over both x and z. And the reason we are doing, I'm writing this out is, this integral just ends up being a Kullback-Leibler divergence between the Gaussian q and p of z, which is the standard Gaussian, for which we can actually write out formulae. And so the loss function that we use to learn phi is going to be the sum over all of the training data of the Kullback-Leibler divergence between q and the standard Gaussian, q computed at that x, minus the sum over all of the completed data of the log of the probability of x given z, which is a Gaussian. So I've just written this formula out here. This ends up being a function of phi. This first term here is this Kullback-Leibler divergence term. The second term here is this guy here. And there are some extra terms which are not functions of theta, so we can ignore, of phi, so which we can ignore. And you can simplify this further by assuming that the D matrix is diagonal. That gives you this reduced formula for L. And so to estimate the parameters of the encoder, which approximates the posterior probability of z given x, we have this loss function that you can minimize with respect to the function, to this term p, and you can do this using gradient descent. I haven't spent a lot of time working on the going over the arithmetic. This is just to sort of gloss over the math. I don't see a lot of value in spending going through the mathematical details in a lecture. I think that's best handled offline. You should go through the slides, but you get an idea of where all of these things come from. And so here is the complete training pipeline. You want to estimate a nonlinear Gaussian model for x. So the generating model is this term, that you have some z, which is transformed by this nonlinear function, and then you add noise. To train the data model, you initialize theta, then you're going to, and at the first step, you need to have the posterior probability of z given x to sample z from, but you don't have it. So you're going to approximate the posterior probability distribution by this Gaussian with a mean which is a function of x and a variance which is a function of x, and you're going to sample z from it. Then once you have the z, you get a loss function that you can minimize to estimate the parameters of theta. Once you've estimated the parameters of theta, you can pass derivatives right through, and you can now update the parameters of phi to give you a better approximation of the posterior probability of z given x, which is this guy here. And so now you update the parameters of phi. So there are two distinct steps here. One where you sample z and then you update this guy. And then having updated it, you use this one to pass the derivatives through to update these phi. You can merge the two into a single step and say, I have a common loss function. So I have two separate loss functions, one that I'm using to minimize this, to estimate theta, and a separate loss function which I'm using to estimate phi. I can sum the two loss functions up because they're two independent loss functions, and I can jointly optimize them, which says that now I have a single loss function, which is a function of theta and phi, and the noise over here, which is this guy. And now within each step, I can just sort of compute derivatives for this combined loss function with respect to theta, phi, and this covariance matrix to estimate my parameters. So this is the whole process. So the process here is this again. I'm going to start off by estimating, initializing all of my parameters. Then I'm going to sample a bunch of z. I could just sample one z per x. It doesn't matter. This completes the data. Then using the completed data, I can define this loss function, which combines the loss for this guy and this guy, and then use gradient descent to update both theta and phi. And once I've updated both theta and phi, I can use this lower decoder portion again to resample Z. So once again, I've recompleted my data and I can repeat the process. And eventually, I'm going to learn all the parameters of the network. And once I've trained it, remember what I really was interested in is this nonlinear Gaussian model, just the decoder. So I'm going to throw away everything at the bottom. And if this is a generative model for my data. And generating data using this part of the model should ideally give me data similar to X. That's about it. And where do the neural networks come in? This is modeled by a neural network. And the function that estimates the mean and the variance for this Gaussian that approximates P of Z given X, that too is usually a neural network with two outputs, one of which is the mean and the other which is the variance. So that's where the neural networks come in. So this is the decoder, this is the encoder, this entire thing is the variational autoencoder. The decoder is the generative model. The encoder is only needed for training, but you can also use it to learn the approximate distribution of Z given X once the whole thing has converged. And this value Z itself is a latent space representation of the data. So you can use the encoder to obtain you're going to get a distribution for the latent space values of Z. And if you take the mean can be thought of as the expected value of the latent representation of X. So the encoder can be used to obtain latent representations of X from Z, latent representation Z from X. The decoder is actually a generative model that, given any Z, is going to generate some X, which approximately follows, looks as if it was drawn from the true distribution of the data this model was trained from. So that's the VAE. The issue with VAEs, they are strictly generative models. They can only be used to generate samples of the data. They can't really be used to compute the likelihood of data, at least not directly, because P of X is intractable. But as generators, they are very, very effective. They can learn very complex distributions. For example, this was from Calder's paper, where he learned a VAE to learn the distribution of MNIST digits. And you can see that when you generate samples from the VAE, it ends up looking like MNIST digits. Or this was a VAE trained from a few faces, and then you just feed it random values of Z and draw samples from it, and you can see that it actually generates faces. So basically, this network has learned the curved manifold in this pixel space where the data lie, and it's only generating data within the face manifold. Very pretty, right? So, and what about Z? The Z often captures the underlying structure of the data X in a smooth manner. I mean, going back to the helix example, Z is going to learn the position on the helix, right? It's going to learn for any X, you're going to know where on the helix that data instance was obtained from. So more generally, if you've got something like say faces may lie on some curved manifold, right? If faces lie on a curved manifold, then any face basically is some point on this manifold plus some noise. So if I'm given two faces, and if I find the center of the distribution of Z, if I find the expected value of Z given X, which is, mu of X phi, right? For each of the two faces, then as I vary Z, I'm basically going to be traveling along this manifold. We know this, right? Just as in the helix, as I vary Z, I'm just going along this curve, and then that position is put through the decoder to generate the actual position on the helix. So here for the faces, if I took this Z for the first phase and took this Z for the second phase, and then I varied Z, so this is in the Z space, the whole thing is going to be straightened out. And the encoder, the decoder is what is folding the sheet. So this guy would be here, this guy would be here. As I vary Z along this point, they're going to, after you put that Z value through the decoder, you're going to end up at some point here, which is going to look like a face that is intermediate between the two faces. So you can see that how people have used this to start off with different faces to get one neutral face, you get a happy face, you get the Z for these two guys, find an intermediate Z and put it through the decoder. You end up with a face that's kind of smiling. You get a neutral face, a very unhappy face, take an intermediate Z, it ends up looking like a somewhat unhappy face. So all of these things become possible. So to conclude, VAEs are simple nonlinear extensions of linear Gaussian models. They are excellent generative models for the distribution of data. There are various extensions like conditional VAEs, which model conditional distributions like P of x given y, which is all very straightforward extensions, where the conditioning variable y is an additional input to both the encoder and decoder. They've been successfully embedded into, because now it's a generative model, you can embed this whole thing into more complex generative models, like even hidden Markov models. All that happens is that there's nothing about the whole model which says that this guy must be Gaussian. You could change the Z to have any kind of distribution. This could be the output from an HMM. This could be a Markov chain. You can do all kinds of things with Z. And so as a result, you can extend this model very trivially by having different kinds of structures for P of Z, like a Gaussian mixture or a Markov model. And all of these end up with give you interesting models where the learning itself remains very similar to what you've just seen here. So there's a vast topic on the subject. I highly recommend that you read it. And that's it. That's the last official lecture for this semester. So any questions, guys?